Welcome to session 4, where we look at cable testing. Networking media is a backbone of any network. Networking media is literally and physically the backbone of a network. Inferior quality of network cabling results in network failures and unreliable performance. Copper, optical fiber, and wireless networking media all require some form of testing to ensure that they meet the strict specification guidelines. These tests involve certain electrical and mathematical concepts and terms such as signal, wave, frequency, and noise. These terms will help you understand networks, cables, and cable testing. At the end of this session, there are a number of things you should be able to do, and these are shown in the slide. We'll cover a few key topics, which includes frequency-based cable testing, signal and noise, and the reading material is shown on the slide. Now, frequency-based cable testing. Attenuation, which is signal deterioration, and noise, which is signal interference, can cause problems in networks because the data sent may be interpreted incorrectly or not recognized at all after it has been received. Proper termination of cable connectors and proper cable installation are therefore important. If standards are followed during installation, repairs, and changes, attenuation and noise levels should then become minimized. It is helpful to think of waves as disturbances. Ocean waves can be described in terms of their heights or amplitude. The period, so a wave is an energy that travels from one place to another. The period of the wave is the amount of time between each wave, measured in seconds. Networking professionals are specifically interested in voltage waves on copper media, light waves in optical fiber, and alternating electric and magnetic fields called electromagnetic waves. The amplitude of an electrical signal represents height, but it's measured in volts instead of meters. The period is the amount of time it takes to complete one cycle, and this is measured in seconds. The frequency is the number of complete cycles per second, and this is measured in hertz. If a disturbance is deliberately caused and involves a fixed predictable duration, it is called a pause. However, if that disturbance is not deliberately caused, then you can guess what it is. It is noise. Pulses are an important part of electrical signals because they are the basis of digital transmission. The pattern of the pulses represents the value of data being transmitted. Sine waves or sinusoids are graphs of the mathematical functions. Sine waves are periodic, which means that they repeat the same pattern at regular intervals. Now, for the particular sine wave shown, we can see the amplitude and the period. Square waves, like sine waves, are also periodic. However, square waves graphs do not continuously vary with time. They represent digital signals or pulses. Like all waves, square waves can be described again in terms of amplitude, period, and frequency, and those are shown on the diagram. The period is indicated as T, the amplitude as A. Now, we've come across the number systems. There are three important ones that are used in networking: the base 2, base 10, and the base 16. Numbers with exponents are used to easily represent very large or very small numbers. Many cable testing calculations would involve numbers that are very large and require the use of exponents. To make this easy, logarithms is used, or the log. The laws would sort of linearize this and convert these huge numbers into numbers that are manageable. A particular terminology is associated with logarithms, and this is called the decibels, and it's measured signal intensity, and it is a measured signal intensity on copper, optical, or wireless media. There are two formulas that are used to calculate decibels. That is the power one and the voltage one. The power one is 10 log to base 10 P initial, that's the initial voltage value, the final voltage value over the reference power value. So again, there are two forms of measuring, formulas for measuring decibels, the power one and then the voltage one. The power one is 10 log to base 10 final power over the reference power. Then the second one is 20 log final voltage over the reference voltage. My question to you is, why is one 10 and the other 20? The answer to this will lie in the relation between what? Power and voltage. If you know that relation, then you'll be able to answer the question why the voltage formula has a 20 rather than a 10. dB represents the loss or gain of the power of a wave. Decibels can be negative values which will represent a loss in power as a wave travels on a positive value, or a positive value to represent a gain in power if the signal is amplified. So normally we use the power formula to measure light waves on optical fiber. The voltage formula is used to measure the electromagnetic waves on copper cables. There's an example there for you to consider. If the source power of an original laser is 7 microwatts and the total loss of a fiber link is 13 dB, how much power is delivered? It's a simple substitution into formula, and it shouldn't take you more than 3 minutes to work out. How do we view signals in time and frequency domain? Characters, words, pictures, video, or music can be represented electrically by voltage patterns on wires and electronic devices. Now, we use an instrument called an oscilloscope. It's an important electronic device which is used to view electrical signals such as voltage, waves, and pulses. Of course, you cannot see these things with your physical eye. So it's this device that helps you to see it. The analysis of the signals with an oscilloscope is called time domain analysis because it shows the signals within the time domain. The x-axis is time. Engineers also use frequency domain analysis to study signals. And here, the device creates there's a special device called a spectrum analyzer, which creates a graphs for frequency domain analysis. Here, the x-axis is in frequency, and that is why we call it a frequency domain analysis, as opposed to our time domain analysis. If you consider a single frequency electrical sine wave whose frequency can be dictated by the human ear, if this signal is to be transmitted to a speaker, a tone will be heard. Now imagine a combination of this. This will create a complex wave, something which is not a pure sine wave. This signal will then contain, or tone will contain, several tones. A graph of the tones will show several lines that correspond to the frequency of each tone. The question is how do unwanted signal, which is noise, affect the main signal? Noise is an important concept in networks such as LANs. Noise usually refers to what? Sounds. However, noise related to communication refers to undesirable signals. Noise can originate from natural or technological sources and is added to the data signals in the communication systems. All communication systems have some amount of noise. Even though noise cannot be eliminated, its effects can be minimized if the sources of the noise are understood. The main thing to carry away from this slide is that noise is an unwanted or undesirable signal, and it cannot be eliminated, but its effects can be minimized. There are many possible sources of noise, like we said. These can be nearby cables that carry data signals. They can be RFI from other signals that are being transmitted nearby. It can be EMI from nearby sources such as motors and lights, Laser noise at the transmitter or receiver of an optical signal. So those are all forms of sources of noise. Now, the noise that affects all transmission frequencies is called white noise. Noise that only affects a small range of frequencies is called what? Narrowband or interference. Narrowband interference. White noise on a radio receiver would interfere with all radio stations because it affects what? All wavelengths. Narrowband interference would affect only a few stations whose frequencies are what? Close together. When detected on a LAN, white noise could affect all data transmission, but narrowband interference might disrupt only certain signals. So it's important to distinguish between what? White noise and what? Narrowband noise. Another form of noise that I would mention is thermal noise. And I leave it to you as an exercise to find out what is thermal noise. Analog bandwidth typically refers to the frequency range of an analog electronic system. The unit of measurement for analog bandwidth is hertz, the same as the unit of what? Frequency. Digital bandwidth actually measures how much information can flow from one place to another in a given amount of time. The fundamental unit of measurement for digital bandwidth is what? Bits per second. Let's talk about signal over copper and fiber optic cables. On copper cables, data signals are represented by voltage levels that represents binary ones and zeros. The voltage levels are measured based on a reference level of 0 volts at both the transmitter and the receiver. For a LAN to operate properly, the devices that receive data must be able to what? Accurately interpret the binary ones and zeros transmitted as voltages. Two basic types of copper cable are the shielded and unshielded. In shielded cable, shielding material protects the data signal from external sources of noise and from noise generated by what? Electrical cables with signals within the cable. Think back to the coaxial cable, the picture of the coaxial cable that we saw earlier on. Coaxial cable is a type of shielded cable which consists of a solid copper conductor surrounded by insulating material and braided conductive shield, and then an outer jacket. The braided shielding is electrically grounded to protect the inner conductor from external electrical noise. Fiber optic cable increases and decreases the intensity of light to represent what? Binary ones and zeros in data transmission. Optical signals are not affected by electrical noise, and optical fiber does not need to be grounded unless the jacket contains a metal or metallized strength member. What does that mean, a metallized strength member? First of all, to answer that question, think about the nature of an optical fiber. The fact that it is quite weak, it is something that is fragile and needs to be protected. So the metallized strength member is something that is put in there to sort of give it some strength and protect it from damage. As costs decrease and speeds increase, optical fiber may become a more commonly used LAN media. Attenuation and insertion loss. Attenuation is the decrease in signal amplitude over the length of a link. Long cable lengths and high signal frequencies contribute to greater signal attenuation. So as the signal propagates along the cable, its strength decreases, and we refer to that as attenuation. Attenuation is expressed in dBs with negative numbers, meaning loss. Smaller negative values are indication of a better link performance. There are several factors that should contribute to attenuation. The resistance of the copper cable converts some of the electrical energy to the signal of the signal into heat. Impedance is a measurement of the resistance of the cable to alternating current and is measured in ohms. The normal impedance of a category 5 cable is, say, 100 ohms. Now, what is a category 5 cable? If a connector is improperly installed on a category 5, it will have a different impedance value than the cable. This is called an impedance discontinuity or an impedance mismatch. Impedance discontinuities cause attenuation because a portion of the transmitted signal will be reflected back like an echo and does not reach the receiver because of the discontinuity. Remember, the signal is traveling across. So if there's a discontinuity, it cannot get there, so it gets reflected back. And that will be perceived as an echo. This makes it difficult for the receiver to detect data values, and it's called jitter, and results in data loss. A combination of the effects of signal attenuation and impedance discontinuities on communication link is called insertion loss. So to give you a formal definition of jitter, it is the variation in time, it is a variation in the time between packets arriving caused by what? Network congestion. Sources of noise let's look at sources of noise in copper cables. Noise is any electrical energy on the transmission cable that makes it difficult for a receiver to interpret the data sent from the transmitter. Crosstalk involves the transmission of signals from one wire to a nearby wire. So crosstalk can also be caused by signals that's on separate or nearby cables. When crosstalk is called by a signal on another cable, it is called alien crosstalk. Crosstalk can be more destructive at higher transmission frequencies. So what do cable testing instruments do? They measure crosstalk by applying test signal to one wire pair. In twisted pair cable is designed to take advantage of the effects of crosstalk in order to minimize noise. In twisted pair cable, a pair of wires is used to transmit one signal. Twisted wire pairs in a cable are also more resistant to crosstalk or noise signals from adjacent wire pairs. There are three types of crosstalk. There's a near-end crosstalk, there's a far-end crosstalk, and there's a power sum near-end crosstalk. The near-end crosstalk is computed as a ratio of the voltage of amplitude between the test signal and the crosstalk signal when measured from the same end of the wire. This difference is then expressed in a negative value of decibels for the link. Low negative numbers indicate more noise, just as low negative temperatures indicate more heat. To verify proper link performance, nests should be measured from both ends of the link with a high-quality test instrument. Of course, because of attenuation, crosstalk occurring further away from the transmitter creates less noise on a cable than nest. This is called the far-end crosstalk. The noise caused by far-end crosstalk still travels back to the source, but it is attenuated as it returns as well. First, this far-end crosstalk is not as significant a problem because when it's at the other end, then it gets reflected back, and then it's attenuated further, and therefore, doesn't pose much of a significant problem. The power sum nest measures the cumulative effect of nests from all wire pairs in the cable. Remember, in any cable, there can be several wire pairs, so the power sum measures the cumulative effect of all these cables. The power nest is computed for each pair based on the nest effects of the other three pairs. All cable links must be tested to the maximum rating that applies for the category of cable that is being installed. There are 10 primary test parameters that must be verified for a cable link to meet the TIA standards. And this wire map, insertion loss, near-end crosstalk, power sum crosstalk, equal level far-end crosstalk, power sum equal level far-end crosstalk, return loss, propagation delay, cable length, delay skew. These are the 10 parameters that must be verified for any cable link. So when you are doing that, you need to check on these 10 things. The wire map test ensures that no open or short circuits exist on the cable. A short circuit occurs if two wires are connected to each other, which shouldn't be connected. And this a short circuit is something that gives you a sort of a spark when you touch some wires together. We call that a short circuit. The Ethernet standard specifies that each of the pins on an RJ45 connector have a particular purpose. The NIC transmits signals on pins 1 and 2 and receives signals on what? Pins what? 3 and 6. Would that help explain why the different types of connections, remember, crossover cables, rollover cables, and straight-through cables? The wires in an unshielded twisted pair cable must be connected to the proper pins at each end of the cable. Propagation delay is a simple measurement of how long it takes for a signal to travel from the cable to the, along the cable that is being tested. The delay in a wire pair depends on its length, twist rate, and electrical properties. Propagation delay measurements are the basis of cable length measurements, not the actual length, because if you twist the wire pair, then the actual length will be different. The length you measure will be different from the actual length of the cable, and that is why you use what? A propagation delay. TIA EIA specifies that the physical length of the link shall be calculated using the wire pair with the shortest electrical delay. Then there's a concept of what? TDR, which is time domain reflectometry. This test is used not only to determine the length, but also to identify the distance to wiring faults, such as shorts and opens. The propagation delays of different wire pairs in a single cable can differ because of the differences in the number of twists and the electrical properties of each wire pair. The delay is called delay skew. If the delay skew between the pairs is too great, they arrive at different times and data cannot be what? Properly reassembled. A fiber link consists of two separate glass fibers functioning as independent data pathways. One fiber carries transmitted signals in one direction, while the second carries signals in the opposite direction. External electromagnetic interference or noise has no effect on fiber cabling. Why? Attenuation does occur on fiber links, but to a lesser extent than on copper cabling. Because noise is not an issue when transmitted on optical fiber, the main concern with optical fiber is the strength of the signal, of the light signal that arrives at the receiver. If attenuation weakens the light signal at the receiver, then data errors will result. Testing fiber optic cable primarily involves shining a light down the fiber and measuring whether a sufficient amount of light reaches the receiver. On a fiber optic link, the acceptable amount of signal power loss that can occur without dropping below the requirements of the receiver is always calculated. This calculation we call the optical link loss budget. This then brings us to the end of this session where we discuss the important issue of cable testing. Thank you.